Our first speaker today is Vinoda B. Patil, Nagaraj Shetty, and Suresh Kumar. I don't know who is presenting from the Department of Chemistry, Karnataka Science College, Dharwad. And the title of their work, which they are presenting today, is Nanostructured zinc oxide based electrochemical sensor with an ionic surfactant for the electroanalysis of trimethoprim. So, who is going to be presenting this, please?
Vinoda, Mr. Vinoda.
Myself, Vinoda Patil. I am pursuing PhD under the guidance of Dr. S.M. Tuwar, Associate Professor, Department of Chemistry, Karnataka Science College, Dharwad. Presenting my topic is nanostructure zinc oxide based electrochemical sensor with anionic surfactant for the electroanalysis of trimethoprim. The presenting work contains the contents starting introduction, experimental parts, result and discussions, conclusions. This is the graphical abstract of our present work. Introduction. Trimethoprim is an antibacterial medication used to prevent and treat infection of the urinary, intestinal, and respiratory tract. Antibiotics like trimethoprim are given to humans and animals in a vast quantities every year to cure the prevent illness and infections. The main objective of this work is to develop electrochemical sensor of a simple, highly sensitive and stable method for the detection of trimethoprim and also applying it to the clinical and biological samples. This is the experimental part of our present work. Trimethoprim was purchased from Sigma Aldrich and 0.1 millimolar standard solution of trimethoprim was prepared in the dissolving using double distilled water. Phosphate buffer solution were prepared in the ranging of 3 to 11.2 as a supporting electrolyte. Throughout the experiment, double distilled water was used and all chemicals were used in the analytical grade. The instrumentation of our electrochemical workstation was used. The voltammetric measurement were
Vinota,
carried
I
out
cannot
in
see your slides moving, please. It is just on the first slide. I cannot see the slides move.
Ma'am, slides are moving. I think there is some technical internet problem at your end. Kindly check.
The slides are, this is just one slide which is there. I cannot see any other slide moving.
Ma'am, we can see the slide moving. Yeah.
I can't. Okay, please go on.
Yes.
Are you recording?
Yes, ma'am. We are recording the session. Yes, ma'am.
Okay, now I can
Yes,
see the slides. Yeah. Okay, fine.
Okay, ma'am. Please
Go ahead. Yeah, please go ahead now.
Okay. The voltammetric measurement were carried out in a 10 ml single compartment consisting of a 3 electrode system. Here we are used working electrode as a zinc oxide based anionic surfactant with a carbon paste electrode, AgAgCl electrode as a reference electrode, and platinum wire as a counter electrode. Results and discussions of our present work, the surface area of a sensor and characterization of a present work, the varying cyclic voltammograms at varying the sweep rate for a trimethoprim regarding the 1 millimolar KTFeCN6 is dissolved in a 0.1 millimolar 0.1 molar KCl. Using a Randall-Sewick equation, calculated the surface area of the working sensor. These are the characterization of a present work. AFM, atomic force microscopy, that gives the total area roughness of the bare as well as zinc oxide based carbon paste electrode. The XRD pattern of the prepared zinc oxide nanoparticle that gives the reveal the strong diffraction phase of a zinc oxide exhibiting the hexagonal root-like structure. The SEM analysis was also gives the irregular shape and size of the zinc oxide nanoparticle. This is the comparison voltammogram of the trimethoprim comparing with the bare carbon paste electrode as well as modified sensor. These are the voltammogram. In these, all voltammogram gives the only oxidation peak, no reduction peak. Hence, its process was irreversible. It displays the anodic peak at a 1.280 volt with a 153.9 microampere for the zinc oxide base anionic surfactant with the carbon paste electrode. Accumulation time was also studied. Experimental performed in the range of 0 to 70 seconds. Plot of accumulation time versus peak current suggests that the 10 second is optimum for the further studies. And effect of pH was also studied. This is the voltammogram of different pHs starting from 3 to 6.0 pH. In the potential range 0.8 volt to 1.4 volt. By these voltammogram, plot the graph of E versus pH that gives the slope value 0.0219, that is nearly equal to the 0.021, that shows the uneven number of proton and electron involved in the electrochemical process. Effect of scan rate was also studied. This is the voltammogram of a scan rate while varying the 10 millivolt per second to the 410 millivolt per second. Plot the graph of IP versus scan rate that gives the linearity of the voltammogram changes. And also plot the graph of log IP versus log mu that gives the slope value 0.384, that is nearly equal to the 0.5, that shows the process was diffusion controlled. And also plot the graph of EP versus log mu using the Leveron equation, calculate the heterogeneous rate constant as well as number of electron transfer in the electrochemical process. Variation of concentration was also studied, varying the concentration of 0.8 micromole to 10 micromole. This is the voltammogram gives. And from these voltammogram, plot the graph of IP versus concentration that gives the linearity range. Using the equations, LOD, LOQ was also calculated 2.58 into 10 raised to minus 8 mole as well as 8.61 into 10 raised to minus 8 mole respectively. This is the comparison table of earlier reported work as well as present work. The sensor assembly displayed the lowest limit of detection values compared to the others. Therefore, our method is convenient, sensitive, and reliable. Analysis of a trimethoprim in a tablet by the differential pulse voltammetry and recovery was also studied. The recovery obtained 99.36%. And also study the application of a differential pulse voltammetry for the determination of trimethoprim in a spiked human urine sample. Excipients was also studied. The biological samples consist of several metabolites. The study of excipients was carried out the modified electrode sensor using the trimethoprim of 0.01 millimolar and excipients of 0.1 millimolar concentration. Our experimental results, excipients do not alter the voltammetric response of the trimethoprim. And lastly, conclusions. The use of zinc oxide nanoparticle based with the sodium dodecyl sulfide carbon paste as an electrode material has made a new development of a sensor for the determination of trimethoprim. Voltammetric response was an excellent zinc oxide based anionic surfactant for the carbon paste electrode in a pH 3.0 to the nascent bare carbon paste electrode. The electrode process was irreversible, gives an oxidation peak. Effect of pH shows the role of proton transfer in the electrochemical process. The present result with the reference to the diffusion controlled reaction involve the 1 proton and 2 electron transfer at a working sensor. Limit of detection was calculated 2.58 into 10 raised to minus 8 mole. In addition to this method of applicable for the clinical and biological samples. These are the references. Thank you.
Thank you, Vinoda, for a very nice presentation. Now the session is open for any questions. If any queries, if somebody has, can raise them, please. Any questions? Okay, in that case, if there are no questions, I think we will thank Vinoda for a very wonderful presentation, and congratulations for the excellent work which is embodied in this presentation. Thank you.
Thank you, ma'am.
Thank you so much.
Thank you, ma'am.
Yeah. So thank you, Vinoda. Now we will request the second presenter for the day, Dr. Ravinder Pal Kaur Sodhi and Dr. Gurpreet Kaur from the Government College of Women Parade, Jammu. And the title of the presentation is Organic Inorganic Composites, a Sustainable Approach for Greener Synthesis. Can I request the participants other than the speakers, please, to mute? And Ravinder, can you please start with your presentation?
Yes, sure, ma'am. Sure, ma'am.
Thank you. We're waiting.
Is the screen visible, ma'am?
Yes, it's visible to me. Thank you.
Okay. Is the screen visible?
Yes, it's visible, Ravinder.
Okay.
Thank
A
you.
very good afternoon to you, ma'am.
Good afternoon, Bachi.
And good afternoon to listeners also. So today I'm here to present my work, that is Organic Inorganic Composites, Sustainable Approach Towards the Greener Synthesis. So the development of heterogeneous catalysis for the chemical synthesis has become a major area of research over their homogeneous counterparts due to its potential advantages like activity, selectivity, their simplified recovery and reusability. And almost 90% of all the chemicals that are synthesized, they use catalyst during their processing. And the catalysts are indispensable in the production of bulk and fine chemicals and prevention of pollution by avoiding the formation of waste. And the significance of this catalysis has been, and its proven impact on the science has been recognized by several Nobel Prizes in chemistry. In 1909, for catalysis and fundamental principles governing the chemical equilibrium and the rate of reaction. In 2001, for asymmetric hydrogenation and oxidation. In 2005, for metathesis. In 2010, for cross-coupling reactions. And 2021, for asymmetric organocatalysis. Organic and organic composites also emerged as an important tool for attaining the new generation chemical technology, paying particular attention on the development of these supported metal catalysts. So there are majority of sport materials where they can be applied in catalysis, which can be based purely, they are inorganic in nature, where the sports, they require high temperature calcinations and polymerization, or they can be simple biomaterials since they are suitable supports for many reagents and catalysts, since they offer the advantages of being renewable, biodegradable, as well as being cheap and low toxic. So what we do here is that we take a homogeneous catalyst and we incorporate or immobilize them on a support material, which can be through a physical adsorption or through a chemical bond. So keeping in this context, what we have done is that we have prepared a series of different metal acetyl acetonate complexes, and they were covalently anchored onto the surface of a min functionalized silica starch composite via surface functionalization with 3 amino profile silica starch composite, followed by their Swift condensation of these amino groups, these Swift condensation of these amino groups with the acetyl acetonate complexes. And these metals can be cobalt, copper, palladium, ruthenium, manganese, and copper. So what we did here is that we started with the silica. We took activated silica. We treated activated silica with thionyl chloride. That is, we added thionyl chloride dropwise over a period of 15 minutes at room temperature, followed by stirring for 15 hours at 80 degrees. And the resulting, unreacted thionyl chloride was removed by distillation, and the resulting silica chloride, this is the resulting silica chloride, this was then vacuum dried at 90 degree. Then the next step was the next step is then the formation of silica starch composite. What we do here is that we take silica chloride. To this we add cornstarch and triethylamine using chloroform as a solvent, and the reaction was refluxed for 10 hours, and then the mixture was filtered and dried in oven at 120 degree for 2 hours, resulting in the formation of this silica starch composite. Then the functionalization was done, that is AMPTS was added to the silica starch composite. Toluene was used as a solvent, and the reaction was carried out at 120 degree for 15 hours. So finally the product was our amine functionalized silica starch composite. It was dried at 110 degree for 5 hours to give the surface bound these amino groups. These are surface bound amino groups, and the final step was Schiff condensation between these NH2 groups and the metal acetyl acetonate complexes, resulting in the formation of these two types of catalyst. So by incorporating these natural biopolymers in an inorganic material, and hybrid composite of increased stability was attained, which typically exhibited the properties of their initial components. So after synthesizing these different catalysts, their characterization was done. So this is the, I'm going to explain the characterization of one of the catalysts. So I have chosen cobalt acetyl acetonate supported onto amine functionalized as the catalyst. So this is, first is the FTIR of the catalyst. The IR spectra showed a band in the region of 32 to, the FTIR spectra showed a band in the region of 37 to 3200 centimeter inverse, which were assigned to the surface OH groups. And after the functionalization with aminopropyl trimethoxysilane, some slight changes were observed in the spectrum, and the new bands appeared at 2932, which were due to the CH2 stretching vibration of the propyl group. And the NH2 groups, the NH2 stretching vibrations, they overlapped with OH vibration bands. And after the complexiation of these NH2 groups with metal acetyl acetonate complexes, a characteristic C double bond N bond appeared at 1646. So this is the FTIR of one of the catalysts. Then the next study was our TGA. TGA is our thermogravimetric analysis, which gives the thermal idea related to the thermal stability of the catalyst. So as we can see here, there is a major weight loss from 230 to 480 degrees Celsius. That is due to the decomposition of starch or the soft material, that is aminopropyl group. So it is safe to carry out the reaction up to 200 degrees Celsius. Then this is the SEM image of the catalyst. As we can see here, the SEM image show a somewhat woolly cloud-like clusters with the a spherical morphology with the particle size of 13 to 18 nanometer. And after the complexiation, what we see is there is a slight roughening of the surface of the catalyst, which may be due to the interaction of our metal complex with the surface of the our support material. Then another is our TEM study, that is transmission electron microscopy. It gives the direct observation of morphology and distribution of metal onto the surface of the composites. It shows whether the metal is in aggregated form or it is distributed evenly onto the surface of the support. So as we can see here that there is no bulk aggregation of the metal. Then after synthesizing these catalysts, our next focus was on evaluating their catalytic activity. So few reactions were catalyzed with these reactions to check out their catalytic activities. So one of the reaction was the thioetherification of aryl halides with thiourea and benzyl bromide in water. So when we talk about CS coupling, so the main problem associated with these coupling is that the use of volatile and these fall-smelling thiols and toxic and flammable solvents that we use, and they lead to the polluting the environment, and they have certain safety problem also. So to eliminate some of these problems, thiourea was used as a source of sulfur, and water was used as a catalyst. So out of the different catalysts we synthesized, the amine functionalized silica starch composite using copper was found to be the best catalyst for the reaction, and water turned out to be the best solvent as it is greener also, and the reaction was carried out at 100 degrees Celsius. So these are the results of different aryl halides that were used for the thiotrification, and the yields are good, and they all were separated through column chromatography. Then a comparative study was carried out in order to check out the role of our catalyst, that whether the catalyst is catalyzing the reaction or there is some sort of role is being played by our support material also. So we carried out the reaction in absence of catalyst and with its precursors also, like silica starch composite, amine functionalized silica starch composite, copper acetyl acetonate in homogeneous medium also, and our catalyst. No doubt the homogeneous condition gave the best result, but they suffer from a drawback like tedious workup, and they are non-recyclable under the reaction conditions. So as we can see here, in the absence of the catalyst, the no reaction was seen, and with our functionalized catalyst with the metal supported on it, the best results were seen. So the use of heterogeneous system was more advantageous over the homogeneous one, being recyclable and easily can be recycled from the reaction medium. So when we talk of heterogeneous catalysis, recyclability is the main topic. So we carried out the reaction for 4 consecutive runs, and as we can see here, there is negligible loss in the activity of the catalyst. So there is another reaction where we evaluated the catalytic activity of our catalyst, that was CH bond oxidations. So what we did here, yes, I can see here. So the CH bond oxidation of aryl alkanes in water. So here the cobalt acetyl acetonate immobilized onto amine functionalized silica starch composite was found to be the best catalyst for the reaction. Different oxidants were used, like oxygen, air, hydrogen peroxide, but TBHP turned out to be the best catalyst for the reaction. And the reaction was carried out under aqueous medium, that is using water as a solvent at 60 degrees. So these are the results of CH oxidation, where different aryl alkanes were subjected to oxidation to aldehydes and ketones. So the results are summarized in the table. So this is the effect of solvent on the CH bond oxidation. As we can see here, we use different solvents like water, toluene, ethanol, acetonitrile, and water turned out to be the best solvent for the reaction. So again, we carried out the comparison of the different precursors. As we can see from the table, the cobalt heterogeneous cobalt acetyl acetonate gave the best results. And recyclability, the catalyst is recyclable up to 5 runs with almost negligible loss in the activity. This is our small contribution in making the environment green and our contribution towards green chemistry. Green chemistry is not a solution to all the environmental problems, but the most fundamental approach towards the prevention of the pollution. Thank you.
A great presentation, Ravinder. Now,
Thank you so
any
much,
questions
ma'am.
from the participants are welcome, please. I'm sure Ravinder will be happy to answer them. It seems there are no queries. So congratulations, Dr. Ravinder, Dr. Ravinder Kaur Sodhi and Dr. Gurpreet for an excellent presentation and very good work conducted. And I congratulate you that you have done such excellent work in the colleges despite the, limited facilities which are available there. And congratulations to the college to be able to provide the facilities to do such excellent work.
Thank you. Thank you so much, ma'am.
Thank you so much.
Thank you.
Ma'am, now
Moving
we
on.
have, ma'am, actually, Dr. Inderjeet and Dr. Sundar Kumari, they are not present in the meeting. So I think Vishram sir is present in the meeting.
Yes, sir. Yes, ma'am. I am present.
Sir, I request you to please wind up your presentation as soon as possible.
Yeah, it will be great if we can do it in time. So is it Mr. Vishram Hiramani?
Yeah. Yes.
Okay, great. You can start with your presentation, please.
Okay.
Thank you.
Is it visible, ma'am? Hello. Hello, ma'am.
Yes, sir, it is visible.
Visible.
It's starting now, yes.
I am audible, ma'am?
You're audible, yes.
Yeah. Thank you. Myself is Vishram Hiramani, research student, Department of Chemistry, Karnataka University, Dharwad. And my research work entitled Exploration of Multifunctional Properties of Paper Petal Leaves Extract Incorporated Polyvinyl Alcohol Oxidizing Starch Blend Films for the active packaging applications. And this work is carried out under the supervision of Dr. Ravindra B. Chowgle, Associate Professor, Department of Chemistry, Karnataka University, Dharwad. These are my contents of my research work. It is subdivided into 5 chapters, mainly introduction, materials and methods, preparation of the polymer blend films, result and discussion, and content 5 is conclusion. And content 4 is subdivided into 10 chapters, which is generally conclude the physico-chemical and biological properties of the polymer blend films. This is the introduction. In the recent years, there is an increasing concerns towards the eco-friendly food packaging material due to the negative impact of petrochemical based polymer towards the nature. The single-use non-degradable packaging materials have widely utilized in food sector, among which only less than 20% are recycled, hence which produce significant damage to the atmosphere. These setbacks can be overcome by producing polymer blend films by PVA starch, which are generally non-toxic and degradable, and offers the new opportunity to develop the novel polymer films with the desirable properties. The main intent of active packaging materials is incorporation of certain additives like plant extract and antioxidant to the polymer films to extend the shelf life of food products. Hence, in the current study, we have selected polyvinyl alcohol and oxidized maize starch as a polymer matrix and better leaf extract as a active component in this study. These are the materials used for the synthesis of the polymer blend films. Polyvinyl alcohol. Polyvinyl alcohol is a synthetic water-soluble polymer prepared by polymerization of vinyl acetate followed by the hydrolysis. PVA is a non-toxic biodegradable polymer with outstanding chemical stability and good film-forming property. PVA is also used for the many applications like drug delivery, packagings, and it's comparatively used for the low-cost production. And this is the structure of PVA. Next material is oxidized maize starch. Generally, oxidized maize starch is prepared by reacting starch with a definite amount of oxidizing agent like sodium hypochlorite and hydrogen peroxide under the controlled temperature and pH. While proceeding reaction, the hydroxyl groups of the starch can be converted to the carbonyl and carboxyl groups. These oxidized starch have unique functional properties such as low viscosity, high stability, and more solubility, good permeability, and also high transparency with excellent film forming ability. Next material is betel leaf extract. Betel leaf, Piper betel is the scientific name of betel, which is commonly available in India, belong to the family of black pepper known as Piperacea. These betel leaves contains large amount of antioxidant like eugenol, ascorbic acid, hydroxysavinol, chaibatol. These leaves are also exhibit excellent antimicrobial as well as antifungal activity. The main objective of the current work is to investigate the effect of betel leaves extract on the physicochemical and biological properties of PVA starch blend films. We have used as PVA and oxidized maize starch as a polymer matrix in this study. This is the preparation of the betel leaf extract. We are procured better leaf from the pre-formed buildings and purchased from the local market,
smallest scope,
Dharwad,
about size
Karnataka.
4. We just use that size 4.
The better leaves were washed with the tap water and then with double distilled water. Moreover, dried at room temperature. After drying, leaves were crushed with the help of mortar and pestle. In that sample, 10 gram of powder samples were dissolved in 90% ethanol for 4 hours and then extracted by the continuously stirring in overnight in the laboratory conditions using magnetic stirrer. The extract was filtered using number one filter paper, and residue remained on the filter paper was transferred into the same beaker and re-extracted until the residue is colorless. And this extract was directly used as a better leaves extract without further purification. This is the presentation of preparation of PVA oxidized mist or better leaf extract blend films, in which we have 1.8 gram of PVA is dissolved in double distilled water on magnetic stirrer at 90 degrees Celsius separately, and oxidized 0.2 gram of oxidized maize starch was dissolved in hot conditions at magnetic stirrer, and that both the solutions were blended in a same beaker and stirred 2 hours for homogeneous blending. Afterwards, the different weight percent like 2 ml, 4 ml, 6 ml, 8 ml of better leaf extract was inserted to the blend solution, and which is stirred on magnetic stirrer overnight to form a clear and homogeneous solution. This homogeneous solution was poured on the Petri dish to obtain a blend film. After solvent evaporation, blend films were peeled out from the Petri dish, and this is the obtained polymer blend film. Result and discussion. First one is FDR spectroscopy. FDR spectroscopy was utilized to know the intramolecular and intermolecular hydrogen bonding interaction between the components of the blend films. Here we see in the PS blend, the peak at 3262 reciprocal centimeter and 1654 reciprocal centimeter is attributed to the stretching and bending hydroxyl groups of PVA and oxidized maize starch. And also peak at 1718 is ascribed to the carbonyl content of the oxidized maize starch. These peaks were after incorporation of better leaf extract, the peak at 3262, which is generally OH peak, which decreased to 3251 after incorporation of the better leaf extract, and also the peaks at 1718, 16454 were decreased to lower wave number. This conclude that the addition of better leaf extract reacted with the polymer matrix through the inter and intramolecular hydrogen bonding, which is shown in the next figure. This is mechanical properties. Mechanical properties are very important criterion for the food packaging films. We are carried out the mechanical properties in which the control polymer PVA and oxidized maize starch blend film shown tensile strength 54.89 megapascal, whereas the elongation break 71.28%. After incorporation of better leaf extract, the tensile strength was slightly increased to 50.31 megapascal and elongation to 79.74% at lower content of better leaf extract. But as the increase in the content of better leaf extract in the blend matrix, the tensile strength goes on decreasing, whereas the elongation of the blend films were increased. This indicates that addition of better leaf extract behaves like plasticizer in the blend matrix. Scanning electron microscopy. Scanning electron microscopy is carried out to know surface morphology of the blend films. The pure PS means PVA oxidized maize starch control films shown a rougher surface with some unequalized holes on the surface of the film. But as the addition of a better leaf extract contributed to smoother the surface with reducing the patches of oxidized maize starch in the polymer matrix, and in which PSB4 blend film shown smoother and homogeneous surface in comparison with other films, which might be due to the better leaf extract in the PS matrix enhance the compatibility, indicating the strong hydrogen bonding interaction occurred among the polar groups of PVA oxidized maize starch and better leaf extract. Water solubility was carried out to know the solubility of the films in the water. And after the incorporation of the better leaf extract, the solubility of the blend film initially decreases, but as the concentration of better leaf extract increases in the blend matrix, solubility also increases. This is due to the increase in the hydroxyl group of the hydroxyl group in the blend matrix due to the addition of betel leaf extract, which term to react with water molecules. Hence, the solubility of the films will increase. The water contact angle was The water contact angle was carried out to know the surface hydrophobicity of the film. Generally, the water contact angle of lesser than 90 degree Celsius termed as hydrophilic, whereas the films with greater than 90 degree water contact angle is termed as hydrophobic. Here, all the films shown water contact angle lower than.
Sir, sorry to interrupt you. Please wind up the results. We are short of time.
Yes. Water contact angle also increased as the betel leaf extract increased in the blend matrix. Water vapor permeability and oxygen permeability also increased as the concentration of betel leaf extract increased in the blend matrix. These are the optical properties we are carried out to know the UV blocking properties of the blend films. In comparison to the control blend, the BLE doped blend films were shown good UV barrier property generally in the region of 200 to 400 nanometer. And the transparency decreases, whereas the opacity of the film increases. This might be due to the addition of BLE in the PS matrix, reduces the polymer interchange spacing, and increases the opacity by permitting less light pass through the film. This is the biodegradation, which is the main backbone of this work. The biodegradation rate was carried out to know the degradation percentage of the blend films. All the blend films shown more than 40%, 30% degradation in 30 days, which means which can be used for the biodegradable packaging, which is promising material to safeguard the environment. Antibacterial activity carried out against the gram-positive and gram-negative bacteria, and in comparison with control film, all control film does not exhibit antibacterial activity, whereas the betel leaf incorporated blend film shown good antibacterial activities. Also, antioxidant properties of the betel leaf extract doped polymer films were enhanced as the concentration of BLE increased in the blend matrix. These are the conclusions. In the present study, eco-friendly biodegradable PVA oxidized betel leaf extract blend films were successfully fabricated by solution casting technique. The incorporation of BLE into PS relatively improved the TS and EB at lower content. Hydrogen bonding interaction among the functional groups of PVA oxidized starch and phenolic compounds of BLE contributes to smooth and homogeneous surface morphology by reducing the patches of OMS particles. Meanwhile, the barrier properties of the films were increased as the concentration of BLE increases. The prepared films were hydrophilic in nature. These bindings were consistent with the increase in the water solubility. Consequently, all the blend films are biodegradable and exhibited good inhibitory activity against both gram-positive and gram-negative bacterial stains. Moreover, films relieved excellent antioxidant properties. These experimental outcomes suggest that the PS blend films containing 2 ml of betel leaf extract has exhibited good physicochemical and biological properties. Hence, it can be utilized for the expansion of active packaging materials. This work is published in the Journal of Polymer and Environment with impact factor 3.1. Thank you. I will thank to Chairperson Professor Meena Sharma Madam and Gurpreet Kaur Madam for giving me opportunity to present my work in this conference. Thank you very much.
Thank you, Vishramji, and congratulations to Dr. Vishram for excellent work which has been done. If there are any questions, I'm sure he'll be happy to answer them.
Yeah.
So since there are no questions and we're already having a paucity of time, so I will just thank Dr. Vishram Hiramani for an excellent presentation. And hope that in the near future, once this pandemic is behind us, we will have the opportunity to host you in an offline seminar. Thank you so much.
Thank you very much.
Ma'am, now we have the last speaker of the session, Mohammad Yasin Sirwal. Yasin sir, are you there in the meeting?
Okay.
Yes, ma'am. Of course, I'm here.
Okay, great. No, Malti is not going to join?
Ma'am, she has some network issue. She's telling me that she is not able to join. Actually, she is speaking from the college.
Okay, that's all right. That's all right.
Actually, she is not able to join. She has been trying since long. So please, I think Yasin sir will present now.
Okay, wonderful. So Mohammad Yasin Sirwal from the Degree College Kishtwar. Please present your work.
Thank you, ma'am. Good afternoon, Meena ma'am and other colleagues.
Good afternoon.
I'm highly indebted and privileged to present here my research work before my teacher, Professor Meena Sharma, ma'am, Ravinder, me, and Gurpreet, we were in the same batch, ma'am. So I'm highly privileged to be over here before you, ma'am.
Yeah. It's a pleasure to listen.
Okay, ma'am. The title of my presentation is one part, three component synthesis of 1,4-dihydropyridines, an anti-cancer molecule. Cancer is one of the leading causes of death across the globe. Lot of drugs are available in the market, which are highly expensive due to their complex mode of synthesis. Various drugs utilized to treat this deadly disease include vinblastine, vincristine, podophylotoxin, Taxol, etc. Introducing our compound, that is 1,4-dihydropyridines, is one such anti-cancer molecule which has proved to be an potent against cancer. We have synthesized this 1,4-dihydropyridines via a special route. This 1,4-dihydropyridine moiety have been recognized as the core nucleus of a variety of drugs used in the treatment of various diseases. We have mentioned so many drugs where this 1,4-dihydropyridine moiety is present as the core nucleus, like we have drugs like amlodipine, nicardipine, benidipine, etc. We can see the structure. These drugs, they have this moiety. This is 1,4-dihydropyridine moiety.
Seen your slides are not moving.
Ma'am, I am moving. I am.
Just move to the slide 2. Yeah, it's okay now.
Okay. So if you can see, all these drugs, they possess a moiety, that core nucleus, that is 1,4-dihydropyridines. These dihydropyridines have been found to be potent.
Yasin, the slides
Yes,
have
ma'am.
not moved for me. Kindly check.
Okay, ma'am.
Gurpreet, please, when you're recording, so I'll see that later. But if it is
Gurpreet?
possible, kindly see
Yes,
that.
ma'am, it is being recorded. You carry on, Yasin.
Okay, good.
It's being recorded, ma'am.
Okay, ma'am. Dihydropyridines have been found to be potent adrenoreceptor antagonists, acting as inhibitors of human prostate contraction, and hence are very useful for the treatment of benign prostate hyperplasia. Recently, these molecules, dihydropyridines, have been investigated for their efficiency in anti-cancer activities. Various routes have been reported for the preparation of 1,4-dihydropyridines, including this thermal and microwave assisted 4+2 cycloaddition. Lakhvinder Singh et al. Reported this. Then we can have this G. Bertolli et al. They have synthesized this. Then this 3-component domino synthesis using CAN, cerium ammonium nitrate, Vora, then a series of other MA, Zolfogil, Safai synthesized dihydropyridines. Means we have a lot of literature over there for the synthesis of this. Our present work, being this important class of pharmacologically active compounds utilized for the treatment of cancer, we present here an efficient, I can say solvent-free, 1-part, 3-component condensation reaction of 1,4-dihydropyridines by treating 1,3-dicarbonyl compound, aromatic amines, and alpha-beta unsaturated aldehydes using SbCl3 over alumina as catalyst, just by grinding at the room temperature under solvent-free conditions. What we did, we carried out a reaction between methyl acetoacetate, cinnamaldehyde, aniline, and 2 mole % of the catalyst antimony chloride over alumina, and this all this mixture was grinded using pestle and mortar under solvent-free conditions. The formation of the spot was noticed by TLC, and finally the structure was isolated, and it was confirmed by various comparison with the spectral details of the known compound. So we took the same protocol and we carried out reaction with a variety of anilines. This is how we prepared the catalyst. This was the reaction. We carried out the reaction between 1,3-dicarbonyl compound, cinnamaldehyde, alpha-beta unsaturated carbonyl compound, aniline, aromatic amine. We prepared this moiety. This is 1,4-dihydropyridine. Important peak. This was characterized by 1H NMR, IR, and mass spectroscopy. This proton NMR spectra clearly shows a distinct peak of doublet and doublet for this 5H proton, which clearly indicates this the condensation has carried out, and this marks the formation of this product 1,4-dihydropyridines. Then we carried out reaction with a variety of anilines, variety of aromatic amines, where this para position was replaced by various groups, sometimes by methyl, sometimes by methoxy, sometimes by electron withdrawing groups. We carried out reaction, and to our surprise, every time the yield was more than 85%. But the time elapsed, it varies from substituent to substituent depending upon their plus I minus I effect accordingly. So here is a table which shows aniline with time elapsed and yield. Then we carried out reaction with toluidine. Then accordingly we replaced that CH3 with methoxy group, fluoro, chloro, and bromo. Accordingly, every time we were getting yield more than 85%. This is how this condensation was being carried out. Normal condensation between aromatic amines and cinnamaldehyde leading to the formation of imine. Then here undergoes 4+2 cycloaddition leading to the cyclization of the product, followed by dehydration, and we are finally getting 1,4-dihydropyridines. Thank you, ma'am, and other colleagues for your patient hearing.
Thank you, Yasin. That was a very wonderful presentation. And if there are any questions, I'm sure he'll be happy to answer them. Any questions, please? So if there are no more questions, I think we can congratulate Muhammad Yasin for an excellent presentation. And thank you so much.
Thank you, ma'am. So nice of you.
Gurpreet, are there any more presentations today?
No, ma'am, that's all for today. That's all.
Okay. So thank you so much, Gurpreet, for conducting this session and also for your support. And congratulations on an excellent conference which you have managed to put together. And thank you, Dr. Avinash. Thank you, Dr. Avinash, for...
Thank you, madam. Thank you very much.
For providing me with an opportunity to, be a part of this very, very conference on a very, very important topic. And congratulations to all. Thank you.
Thank you, ma'am. It's our
Thank you.
pleasure.
Thank you. Thank you, madam, for your cooperation.